the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who have just gone through linear transformations, linear independence, all that stuff. That's kind of the entry to a linear algebra course. And you're just turning the corner and you're talking about the matrix of a linear transformation. Now, honestly, this topic might be optional for some colleges. However, at least in California, it's not optional and it's a cool topic. So we're going to talk a lot about matrices involved in linear transformations. To do so, we're going to start with a conversation about what's called the standard matrix. Now, something to note here, the standard matrix comes from the basic building blocks of the spaces with which we've been talking about so far in linear algebra. And when I say the spaces, I mean like r squared, r cubed, r4, rn, that type of thing. So this topic is actually a future topic, but really helps out to have this conversation here, at least to open the door to it. So the basic building blocks of r squared are these two vectors, e sub 1 and e sub 2, 1, 0 and 0, 1. And it's pretty easy to see that those two vectors will build any vector you want in r squared. In other words, they span r squared. Let's say you have a vector that has components a and b, then that's just a times e sub 1 plus b times e sub 2. Very clean and easy to build a space from those two basic building blocks, which we call the basis for r squared. There are actually an infinite number of pairings of vectors that span r squared, but these two are really unique. They're just very important. Not only are they orthogonal or perpendicular to one another, but they just really make it easy to build a lot of vectors from them. That works nicely with this example. You can easily see that, yes, building AB is very easy using those two vectors. And as I say down there, what makes them so unique? Their simplicity in form. By the way, a similar statement can be made about vectors e sub 1 in r cubed, which is 1, 0, 0, e sub 2 in r cubed, which is 0, 1, 0, and e sub 3 in r cubed, which is 0, 0, 1. Those three vectors will build any vector you want in r cubed. And obviously, you can grow this to n-dimensional vectors, and you can have n of them, and they would span Rn. So let's use this in an example, and you may not think that you're going to be using that, but it actually is true that you're going to be using that. Well, let's suppose that we have a transformation from r cubed to r cubed, and we know that when we apply the transformation to e sub 1, so the vector 1, 0, 0, and when we apply that transformation to that vector, we get an output or an image of 3, negative 1, 2. Notice that I haven't told you what the matrix for the transformation is. We're going to keep that hidden in the background. Likewise, we can apply the transformation to e sub 2. Remember, e sub 2 in 3D, or r cubed, is 0, 1, 0. And its image under our transformation is going to be 1, 1, 1. And finally, the image of E3 under our transformation will be 2, 1, 0. Now the question here, or our task, is to find the image of an arbitrary input from r cubed. That is, if x is that vector right there, x sub 1, x sub 2, x sub 3, our task is to find the image of that x. Well, the trick to this is writing that vector x in terms of sums of these elementary vectors e sub 1, e sub 2, and e sub 3, which for now I'm just going to call the basis vectors for r cubed. So let's go ahead and start there. And I hope you would agree that honestly you could break apart this vector right here into component pieces. It's just x1 times 1, 0, 0 plus x2 times 0, 1, 0 plus x3 times 0, 0, 1. Or in other words, it's x1 times e1 plus x2 times e2 plus x3 times e3. Now, since that's what x is equal to, we'll go ahead and apply the linear transformation to both sides of that equation. That is, we'll look at t of x and realized that we could have rewritten that like this right here and used the fact that our transformation is a linear transformation. They didn't actually say it, but I'm saying it here. It is going to be a linear transformation. And in fact, you probably proved it in the homework for a previous section of material that all matrix transformations are actually linear transformations. So we're going to go ahead and use that idea here. If our transformation is linear, we could write that transformation like this, by breaking it apart across addition and factoring out constants. And I hope you forgive me when I say factoring out constants. It's not that you're factoring at all. You're using a property of linear transformations to write a constant times a vector within a transformation as the constant times the transformation of the vector. Most people say factoring, but it's not. Well, are we stuck or are we not stuck? I'm saying we're not, because we were told whenever we see the transformation of the vector e1, it becomes 3, -1, 2. Likewise, the transformation of e2 becomes 1, 1, 1. And finally, the transformation of e3 becomes 2, 1, 0. So let's go ahead and fill that information in here. Now looking at this right here, notice it is a linear combination of vectors with weights x1, x2, and x3. We know that we can write this actually as a matrix vector product. And pausing right there for a moment, let's read the original question again. Suppose we know T is a transformation, it's linear technically. We know that the transformation acting on E1, E2, and E3 are those vectors. And finally, we're asked to find the image of an arbitrary x in R cubed. Well, technically, I went a little too far. The true image of an arbitrary x in R cubed would be this right here. But I'm so used to actually continuing forward with these types of problems that I just barreled right to the punchline of a different video. But at least we know the image of an arbitrary vector in R cubed will be this right here. However, I love the fact that I did actually continue forward, because notice we ended up with a matrix times a vector in the end. That product is just written over here in blue. So really the highlighted blue statement is actually the answer. That's the image of an arbitrary x. But I want to draw your attention to the fact that we started with the transformation of an arbitrary x, and we ended up finding the true matrix for the transformation. That matrix highlighted in blue is actually the matrix for the transformation. And notice something about the columns of that matrix. They are the exact vectors that E1, E2, and E3 get transformed into. And folks, that's how you would actually build the matrix for your transformation. As long as you know what the transformation does to the basis vectors, which are 1, 0, 0, 0, 1, 0, and 0, 0, 1, then you know your matrix for your transformation. And this theorem here just codifies that statement. Let T be a transformation from Rn to Rm, and let it be a linear transformation. Even though I forgot to write linear in the last problem, that was a linear transformation as well. Then there exists a unique matrix A such that the transformation of a vector is equal to that matrix times the vector for any vector in Rn, where the kth column of A is the transformation of the kth basis vector. That is a vector where it's 0 everywhere except for in the kth position where that is a 1. A little note about notation. Again, E sub k is the kth column of the identity matrix in Rn. Now the proof of this is actually pretty easy. Let x be any vector you want from your domain. So x is in Rn. Then x is the product of the identity matrix with x. It's just like 1 times x. But remember, the identity matrix is a big old matrix, n by n, where the first column is E sub 1, the second column is E sub 2, and so on and so forth until you get to E sub n. And again, we have x right here. Remember, E sub 1 means you have 1 in the first position, zeros elsewhere. E sub 2 means you have a 1 in the second position, zeros elsewhere. And remember, X has n entries, so this multiplication of a matrix times a vector can be written as a linear combination of the columns of the identity matrix having weights the entries in X. So there's nothing wrong with this statement right here, just pure clean logic. Now what do we want to show? Well, we want to show that the transformation of a random vector X is just a matrix A times X, where the matrix A is a bunch of columns of this form, transformation to E1, transformation to E2, and so on and so forth. Well, let's go ahead and perform the transformation of X. So we have the transformation of X is equal to the transformation of that linear combination of the columns of the identity matrix with weights x1 through xn. Because our transformation is linear, that was what we stated at the very top, our transformation is linear, we can break that apart across addition and move those constants in front of each transformation. Now, if you take a look at that, remember, the transformation of a vector is itself a vector. So each of these transformations is a vector. So we have a linear combination of vectors, specifically a linear combination of vectors with weights x1 through xn. And so our transformation of X is actually the product of some weird looking matrix and the vector X. That weird looking matrix, we'll call that the matrix A. And notice each column of A is the transformation of its corresponding column of the identity matrix. So in other words, the first column is the transformation of the first column of the identity matrix. The second column is the transformation of the second column of the identity matrix, all the way to the last column is the transformation of the last column of the identity matrix. And note, that's exactly what we wanted to show. The kth column is the transformation of the kth column of the identity matrix. And so we have finished the proof. Now, something to be said here, I keep having to say the matrix A is the matrix for the linear transformation T. That's a lot of words. I constantly have to say the same thing over and over again. It would be much nicer if I actually had a name for that matrix. And luckily, we do. We're going to call that matrix the standard matrix for that linear transformation. And that's what this definition is essentially stating. So let's go ahead and show this with another example here. Suppose that T is a transformation from r squared to r squared, and it's a linear transformation. And suppose that it first rotates points through -3 pi over 4 radian, or radians if you prefer, and then reflects that point through the horizontal x1 axis. Find the standard matrix. Remember, that's the matrix of the transformation. So find the standard matrix of the transformation. So let's visualize what this looks like first. So we start by looking at the basis vectors for r squared. In other words, E1 and E2. And yes, I get it that I wrote down vector notation, but then I'm saying they're equal. Those vectors are equal to the points 1, 0, and 0, 1. It's that their tips land at those points. Not that big of a deal. Anyway, what we want to do to those basis vectors is rotate them through an angle of -3 pi over 4 radians and then reflect them about the horizontal x1 axis. Just to showcase what this looks like, we have this initial rotation through angles of -3 pi over 4. And now we're going to flip these about the x1 axis to get those two black vectors there, transformation of E sub 2 and transformation of E sub 1. Now there's a lot of action going on here, but I want to show you how to do this in general, not just like, oh, hey, take a look at these now, let's go ahead and figure out what those components are and write the matrix. Instead, actually, I will say that first. So remember, the standard matrix of T is going to be the matrix with column vectors, transformation of E1 and transformation of E2. Let's start with the blue e sub 1 vector that got rotated by negative 3 pi over 4, and its components here are going to be negative 1 over root 2, comma negative 1 over root 2. And then if you rotate that about the x sub 1 axis, it becomes negative 1 over root 2, 1 over root 2. That is the transformation of the e sub 1 vector. Now if we turn our attention to the red e sub 2 vector, that also got rotated by negative 3 pi over 4 radians. Its tip lands at 1 over root 2, comma negative 1 over root 2. And when you flip that about the x1 axis, you get 1 over root 2, comma 1 over root 2. And so the transformation of E2 being the second column of our matrix there, it is 1 over root 2, 1 over root 2, and there is our standard matrix. Now, I would like to show you how to do something like this in general. And to do so, it's going to require a little bit of attention from you and also a little bit of trigonometry. There is our e sub 1 vector, and we know it terminates at 1, 0. But we also know that that point lies on the unit circle. And any point on the unit circle can be listed as an ordered pair of cosines and sines. The x value will be cosine, the y value will be represented by the sine. Simply put, if I wanted to rotate this vector, maybe upwards through an angle of, let's say through an angle of theta, the resulting point would be cosine of theta, sine of theta. So the lesson here, if you're starting with the vector e sub 1, and if you want to rotate that e sub 1 through an angle of theta, the resulting point that you're going to get, or the resulting vector you're going to get, is cosine of whatever angle you rotated it through, comma, the sine of whatever angle you rotated it through. For example, if you're rotating it back through an angle of negative 3 pi over 4 radians, then the x value for that coordinate, or the x sub 1 value, I guess, would be the cosine of negative 3 pi over 4, comma, the sine of negative 3 pi over 4. However, we know the cosine of negative 3 pi over 4 is negative 1 over root 2, and the sine of negative 3 pi over 4 is also a negative 1 over root 2. You could double check my math, but it is true. And that's how I knew that that point was going to be a negative 1 over root 2, comma, negative 1 over root 2. So initially, our transformation of the e sub 1 vector to that negative 1 over root 2, comma, negative 1 over root 2 really was applying the cosine of the angle, comma, the sine of the angle. Simply put, if I wanted a transformation that would rotate our vectors through an angle of theta, well, the e sub 1 vector would rotate to a point cosine of theta, sine of theta. That would be the transformation of the e sub 1 vector. Now, I'm not talking about the flipping about the x sub 1 axis yet. I'm just focusing on how did I get those 1 over root 2s and stuff like that. And how could you do this in general? Now let's talk about the harder case, where we have the e sub 2 vector. Now again, that e sub 2 vector, the tip of it could be represented in terms of sines and cosines. Specifically, the x value would be the cosine of not 0, but pi over 2, because that's the angle you're facing, and sine of pi over 2. I'm going to keep it like that for now. If we want to rotate that through an angle of theta, well then the new point on the edge will not be cosine of theta, comma, sine of theta, because you started at pi over 2. So the new point that you would land at right there would be the cosine of pi over 2 plus theta, sine of pi over 2 plus theta. Again, because you started at the cosine of pi over 2, comma, the sine of pi over 2. So you just want to rotate that a little bit through an angle of theta. Okay, not too bad. However, this could be rewritten a little more cleanly, actually more succinctly here. And the way you do that is using the sum of angles identities from trigonometry. Now, a lot of my handwriting ran into each other, but basically all I did here was exchange this x value, cosine of pi over 2 plus theta, for its sum of angles version. Cosine of pi over 2 cosine of theta minus sine of pi over 2 sine of theta. Likewise, the sine of pi over 2 plus theta, using the sum of angles identity from trigonometry, is sine of pi over 2 cosine of theta plus sine of theta cosine of pi over 2. we happen to know cosine of pi over 2 is 0, so that point can be written as 0 minus the sine of pi over 2, which is 1, times sine of theta, so a negative sine of theta. Likewise, over here, sine of pi over 2 is, again, 1 times the cosine of theta, plus the sine of theta times the cosine of pi over 2, which again is 0. So that second coordinate is just going to turn into the cosine of theta. Now, if you need to take time to digest that, pause the video, because I'm about to erase that. And there we have it. So the second vector, e sub 2, gets mapped to negative sine of theta, cosine of theta. That will be the new coordinates for e sub 2 under the transformation. Again, I want to drive home the point that the first column is a transformation of e sub 1. It's not the transformation that we're looking for, so I'm going to say t bar, because we still have to flip things about the x sub 1 axis, so we're not completely done with our transformation, but it's a partial transformation of our first vector. And the second column is a partial transformation of the second vector. Now think about what happens if you want to rotate things about the x sub 1 axis. So I wrote in there the transformation of the first vector just so that we can have this conversation, and we're going to rotate that about the x sub 1 axis, and when we do, it's just going to put a negative on the y value there. And same thing here, it's just going to put a negative on the y value there. So for the full transformation, now I can just completely erase these bars. The full transformation is going to put some negatives on these y values, and that will work for any rotation. So you're rotating and then flipping about the x1 axis, or in other words, negating the y values. Now you could test this out by plugging in, because we know what we want our transformation to do. We want the standard matrix to be this guy right here. So let's go ahead and see if we had plugged in a rotation of negative 3 pi over 4 radians into this. We want to know, is that the standard matrix for this transformation? And it's not until we plug in the theta. So let's go ahead and plug in the theta and see what happens. Get down to here, I'm just going to go ahead and evaluate each of these trig functions just to let you know cosine of negative 3 pi over 4 and sine of negative 3 pi over 4 are both negative 1 over root 2. And we have negatives times negatives becoming positive. So our transformation matrix, or our standard matrix for this transformation, is basically a matrix full of 1 over root 2's, except for a negative in the upper left hand entry. Let's go ahead and see if that matches what we had earlier. And it does. So what we did for a single case scenario here works for any rotation that I plug in. So if I want to do a rotation of, let's just say, 5 pi over 7 radians and flip it about the x sub 1 axis, I would just substitute into this matrix right here, 5 pi over 7 for theta. In general though, the one that's going to be super helpful for you is the following. That is the general rotation matrix. So if somebody said, hey, I need this transformation to rotate vectors through 7/6 pi radians, or 7 pi over 6 radians, then you just plug in 7 pi over 6 for all these thetas, and that would give you your standard matrix for your transformation. And if somebody said I needed to flip about an axis, then you just need to figure out what to negate here to get your vectors to flip about the appropriate axes. And that usually is done through just a picture like we did in this example. Now I completely understand that this video is a long video. It's just how it works with the standard matrix when you're first learning it. There's a lot of little pieces in there that you're kind of getting used to, but it'll pay off in the long run. So let's read this note. The beautiful part of working with linear transformations is that they are determined entirely by what they do to the columns of the identity matrix. And this is what I've been saying for the past few minutes here, right? Whatever happens to E1 and E2, that will determine your standard matrix. But you can visualize it using images like this if you want to. In R squared, our actions can be seen as actions on the unit square. For example, a reflection through the line x sub 2 is equal to negative x sub 1, So a lot of people have a hard time with that. That's like saying y equals negative x. So a reflection about the line y equals negative x. What that does is it takes the vector that was 0, 1, and it reflects it or rotates it in a way down to negative 1, 0. And again, reflecting e sub 1, which is 1, 0, we know just the reflection will land it here and we'll have the point 0, negative 1 or the vector 0, negative 1. And so the matrix or the standard matrix for that is what it did to e sub 1, the transformation that is, and what the transformation did to e sub 2. Those will be the columns of the standard matrix. And you could do the same thing with a reflection through the origin. It takes the vector 1, 0, and if you're reflecting through the origin, it rotates that 180 degrees to the vector negative 1, 0. And notice that's the very first column of our standard matrix. Likewise, it takes the vector e sub 2, which is 0, 1, reflects that or rotates it 180 degrees to the vector 0, negative 1, and that is the second column of our standard matrix. You could do this all day long. I personally don't view it as transformations of a square, but some students do prefer that visual, so if that works for you, good. In the long run, if you need to compute the standard matrix of a linear transformation, you've got a couple choices. If t is described geometrically, well, you can just compute the transformation on e sub 1 or e sub 2 and so on and so forth, just like we did in the previous example. And when t is described by a formula, fill in the entries by inspection. And that sounds kind of weird, but that is actually our very first example that we did. This guy right here. Our transformation was described by kind of a formula. They told us, oh, when you have when you transform the e sub 1 vector, it becomes this. And when you transform e sub 2, it becomes that. And when you transform e sub 3, it becomes that. And we found out those ended up being the columns of our standard matrix. It's pretty easy to find those. Now, there are other ways you could do this. Somebody might hand you a transformation of a completely different vector than e sub 1. If that's the case, I'll show you how to deal with that at that time. So let's go ahead and just make up a couple transformed vectors. These vectors are transformations of the original basis vectors, but we're going to go ahead and use those new transform vectors to graph the transform of negative 3, 2. Again, we're just making these up, so let's pretend as though the transformation of the e sub 1 vector is 1, 1, and let's pretend as though the transformation of the e sub 2 vector is negative 3, negative 4. And we want to graph the transformation of negative 3, 2. And I would prefer to write that as actually transformation of a vector. Because I told you the transformation of E1 and E2, you actually have the standard matrix for this transformation. Remember, this is going to be some standard matrix times the vector negative 3, 2. But the standard matrix for the transformation is going to be the matrix whose columns are the transformation of E1 and the transformation of E2. And we happen to know those are, just because we made them up, 1, 1, negative 3, 4. So computing the transform of negative 3, 2 is basically a matrix vector multiplication where the matrix is built from the stuff we created. It's very, very nice. There we go, negative 9, negative 11. That's the transformation of negative 3, 2. You could do this all day long. It doesn't take any skill to actually just create two numbers that you want and then create a matrix, the standard matrix, out of those two vectors, and then apply that standard matrix to the given vector because you're taking the transform of that given vector. It's really a very cool way of doing things. Now, in this video, we've done quite a bit of work on standard matrices. They're very important as we move forward, so it's a good idea to get used to them. But what's really important is to understand E1, E2, E3, E4. Those are the basis vectors for Rn. So you do have to get kind of used to those. We'll play with those quite a bit as we move through linear algebra. All right, I've been recording for too long, so you guys have a wonderful day. I hope to see you in the future. Be wonderful humans.
It's the system of equations we must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.